Hey guys, so today we're going to be looking and starting to look at chapter 6, which is looking at the three energy systems and how they relate to ATP. So we're going to go through the first part today, which is looking at the chemical and food fuels and looking how they contribute towards energy production at various intensities. So I encourage you guys to make sure you've got your slides with you. You'll find them in OneNote and also write notes along the way in OneNote under your classwork section. And also then if you have any questions, go into the forum and ask away there. So as I said, chapter 6 is looking at the three energy systems and how they work together to produce ATP, which is the thing that we use for energy. So these are all the key skills and knowledge that we're going to be looking at today throughout this chapter. And the main thing we're going to be looking at today are the fuels, both chemical and food fuels. So we'll look at what the difference are between those two things there. We're going to look at how those fuels are used to, this word here, resynthesis of ATP. So resynthesis is a word that we're talking about putting ATP back together, so putting something back together. We're going to look at how that does this at rest and also during physical activity. So looking how it does it at different intensities. And we'll look at that the relative contribution at those varying intensities. So hopefully by the end of today's lesson, you'll understand that concept a bit more. So the first thing we're going to look at is the role of ATP. So you might have heard of ATP before. ATP stands for adenosine triphosphate. In the exam and SACs, we don't want you trying to spell adenosine triphosphate. So just using this term ATP will be more than okay. So what is ATP? Well, ATP is a chemical that's found in our muscles. And this is the chemical that we actually break down to produce energy. There's no other way to produce muscular contraction in our body apart from ATP. So ATP is really important. Without it, our heart couldn't beat, we couldn't breathe, we couldn't move. So ATP is that molecule that we're after. And ATP is one adenosine molecule attached to 3 phosphate molecules. And so the way we actually create energy for the muscular contraction from ATP is we have our 1 adenosine attached to our 3 phosphates, and to release energy we actually cut off one of these phosphates. So up here, cut off the phosphates, so then we're left with 1 adenosine and 2 phosphates, which is referred to as ADP, adenosine diphosphate, meaning 2 phosphates. And also then we have one little spare phosphate by itself, which is referred to as an inorganic phosphate, or Pi. And by splitting this ATP apart, we release energy. And this energy here can be used for muscular contractions. And as I said earlier on, this is the only way we can actually release energy for our muscles to contract. So we might be thinking that's awesome, we can just do this simple process, but unfortunately things aren't always that simple. We actually only have 2 seconds. Whoa, I went back there. Let's go back again. We have 2 seconds worth of ATP in our whole body. So we can only break down and create energy from our ATP by itself for 2 seconds. So we need to do this thing called resynthesis, or resynthesize our ATP, ADP and Pi here. We need to recreate it back into ATP. And so that's what we're going to be exploring through this. We're going to be looking at how our 3 energy systems can help to put that back together, can help to resynthesize it, and how they work together to do that, which is interplay. So let's just go through what I talked about again with the ATP. So we start off with our ATP here, because it's 1 adenosine and 3 phosphates. So next up, what we're going to do, we're going to split this apart, which leaves us down here. We've got ADP, so ADP, ATP. ADP is here, our adenosine and 2 phosphates, plus energy for contractions in the middle here. And then we have this extra P left, which is known as an inorganic phosphate. So that's the first part. We've released energy for contraction, but because we only have the 2 seconds worth, we want to be putting this ADP and Pi in the middle. We want to make it go back into ATP down here. So that's again where the role of our energy systems come in. Our energy systems can break down chemical and food fuels to recreate, put this ADP back with PI. So again, we've got ATP. So let's have a look at what that looks like. So we might have ATP at the top here. What we're going to be doing, we're going to end up with ADP plus PI. So to get to there, we would have had to break apart one of our inorganic phosphates off, which would leave us here with energy for muscular contraction. So that means we've released energy so we can go for a run, our heart can beat, we can do all those things we need to do to stay alive and move. So then our three energy systems come in to put this ADP and PI back to here, which is what resynthesis is. We're going to resynthesize our ADP and PI back together to create ATP. And what we need here, we need energy from the three energy systems. So that's a circle. It's going to keep on going over and over because we only have 2 seconds worth of ATP. We need to keep on resynthesizing that ATP so we can keep moving and keep exercising. Okay, so now let's have a look at some of those fuels that we might be using to actually break down and resynthesize that ATP. So firstly, we've already talked about the ATP, but it's the major source of muscular contraction. It's the only thing that we can use to actually break it down and make a muscular contraction occur. ATP is 1 adenosine with 3 phosphates. We've ticked that off already. We talked about that. The human body only has a small amount. So as we said, 2 to 3 seconds worth, not very much energy at all. So it's really important we can resynthesize that continually to make sure that we can actually have energy. So we're going to talk about the other fuels now. The first fuel we're going to look at is chemical fuel, and it's PC, okay, or another one known as phosphate creatine. You might also hear of it being called creatine phosphate, but PC, CP, it's all the same thing. Essentially, what this molecule is, it's a P, a phosphate, and a creatine together. So it's a really simple molecule, and it can be broken down. So what happens is we split apart the P and the C, so then we're left with the inorganic phosphate and a creatine, which can then be used to put that ADP and PI back together to create the ATP. We'll talk about that more later on when we get to the next energy system. The next things we're going to look at is food fuel. So obviously this is stuff we're going to get from the food that we intake. So a few of these things, we've got carbohydrates. So we have carbohydrates. It's going to make up quite a large part of our food intake. You can see we've got pasta, we've got breads, we've got some potatoes, some honey, sugars, fruit. That's all carbohydrates. And they're our preferred source of energy during exercise as they require less oxygen to be broken down. And also something really good about these ones is they can be broken down with or without oxygen. So it means they can be used aerobically or anaerobically. The second type of food fuels you can use are fats. So they're the main source of fuel when we're at rest or at submaximal, which are prolonged, long, submaximal, low intensity exercises. They require more oxygen to break down though than carbohydrates. So that's why most of the time we're going to prefer to use carbohydrates. As fats, we need to work at a much lower intensity to actually utilize those. The last food fuel that we can use is protein. When we're talking about protein as a food fuel, we want to be really careful because protein is actually more of a last resort fuel. So let's think more about if we're doing a really ultra endurance event, something like like even longer than Hawaiian Ironman probably. Hawaiian Ironman is you do a 3.6k run, you do a 180k ride, and then you do a marathon at the end. Think even probably more longer events than that is where protein may be being used a bit longer. But the main reason for protein in our diet is actually for the growth and repair of our muscles. So we're not going to be talking about protein so much as a food fuel. The main two are the carbohydrates and fats on the side there.
Okay, so we're just talking about those food fuels, so let's have a look at them a bit more. I encourage you all to kind of have a few suggestions of what foods we could eat that will make up each of those food fuels. So carbohydrates, we're looking at sugars, pastas, breads, things like that. Now, it's really important to use the right terminology as well in your SACs and exams. So carbohydrates is what it's called when it's outside the body. Once we consume it, when it's being digested, it's glucose, but we want to be referring mostly to it as glycogen, because that's a form of carbohydrate when it's stored in the muscles. Fats, again, what's called outside. When we've digested it, it becomes free fatty acids, and then triglycerides in adipose tissue is its main source in the muscle again. Protein, broken down, we've got amino acids, and it gets stored as muscle, and also sometimes fats at various sites. In here, we've got this term yield. So yield refers to how much energy can be produced. So things we'll go over later on, but just briefly mention here. So our yield, so how much, we can see our carbohydrate has enough energy to resynthesize 36 ATP. If we break down fats, a triglyceride, each glyceride has 147. If we break down three of them, has 441, which is a really high yield. That's a really high amount. So you might wonder, why don't we just use fats all the time? Well, the main reason for that is over here. We look at the cost of oxygen. We can see that we require a lot less oxygen to break down carbohydrates compared to fats. And really what that means is that we can work at a higher intensity using carbohydrates compared to when we use fats, where we're going to have to decrease our intensity.
Okay, so this diagram could be a bit confusing for you, but I'll just highlight the main things that I want you to kind of remember. Remember, proteins, not really going to be that relevant for most questions we're going to be getting. It's only for those ultra long distance endurance events, which go for days. Fats, we can only break down fats aerobically, so that means we need oxygen to break down fats. The other important points I want to see is with carbohydrates, we can break down carbohydrates both aerobically and anaerobically. So that's really good to know because it's a really valuable energy fuel, a food fuel, which can be used both with oxygen and without oxygen. With oxygen, we come down here, we don't actually have any waste products really. One of the consequences of using carbohydrates or glycogen anaerobically without oxygen is we end up with some waste products, most specifically hydrogen ions, which are actually going to be what makes us feel sore after doing the 400 meters and cause fatigue and cause us to have to slow down. Okay, so the last concept we're going to go through in this video is the food fuel contribution at different activity levels. So we're going to start off by looking at what happens when we're at rest in terms of our food fuel contribution. So we can see here straight away, I'm sitting down currently. Currently, I'll be breaking down 2/3 fats, and I'll be breaking down 1/3, glucose or carbohydrates. So what that means is when we're at rest, so we're really low sub-maximal intensities, I'm breaking down mostly fats, 2/3 fats, compared to my 1/3 carbohydrates. So when you're at really low sub-maximal intensities, you'll be burning a high percentage of fats. Okay, so as we go from rest and we increase our intensity, we're going to see down here, our carbohydrate's going to start to increase its contribution, whereas our fats will start to decrease its contribution. So the higher intensity we go, carbohydrates start to increase the contribution to energy production and the resynthesis of ATP, and fats will start to decrease. We can see once we get up to our maximum intensity, carbohydrates pretty much are the only way that we can actually provide the only food fuel will provide energy to resynthesize our ATP. So fats, because they require more oxygen, aren't able to contribute towards a resynthesis when we get to higher intensities. If we look over at this table over here, this graph, it looks a bit confusing again, but pretty easy to read once we know what we're looking at. So firstly, down the bottom, we're looking at aerobic power. So this is how hard we're working. We can see when we're at rest, as we've already discussed earlier on up in the top right hand corner, our fats will be about 2/3 at rest contribution, whereas at rest our carbohydrates will be about 1/3 contribution on the right hand side there. as our intensity starts to increase as we plot along this graph more and more, we can see that our fats start to decrease its contribution and carbohydrates start to increase their contribution towards the resynthesis of our ATP. You can see in this part here, which is around about 70% of our maximum intensity, we'll have a crossover where fats actually start going below the contribution and our carbohydrates will start becoming the main provider of our of our energy supply. As we get higher and higher towards the intensities, towards 100, we can see our carbohydrates reach and peak at 100, and our fats will keep on going down to 0. So the real concepts to understand here is that at rest, fats contribute about 2/3 to carbohydrates, which do 1/3, and as our intensity starts to increase, our carbohydrates will become more and more the predominant provider of our carbohydrates, and our fats will decrease. At around 70%, they'll be 50-50, and once you get to maximum intensity, it's all carbohydrates with no contribution from our fats at all due to the high requirement of oxygen that it needs. Okay, and so for our last slide today, we're going to go over something I've already talked about already. So even though fats produce the most energy, so they have the greatest yield, why do we use carbohydrates more? Well, that's because of the amount of oxygen they require. So remember we said fats have the greatest yield, or the greatest amount, so 441 for a triglyceride compared to 36 ATP for a carbohydrate or glycogen molecule. You can see over here, we require a lot less oxygen to break down carbohydrates compared to the fats, which is 5.5 there. So therefore, this means we can work at a higher intensity with our carbohydrates compared to lower intensity when we're breaking down fat. So that's why carbohydrates and glycogen are our preferred fuel source. Okay guys, so that's the end of those first couple of slides about our chemical and food fuels. So what I want you guys to make sure we're doing is, if we go into our OneNote, you can see now Chapter 6 section, Chapter 6 PowerPoint area. We'll be able to see our PowerPoints, and we want you to record your class notes in this section. Okay guys, and the last bit of instructions I've got for you is, firstly, I'll send. You will have got this already in the email because you're watching the video, obviously. But all these instructions here are pretty clear, so read through them. And it's important that over the holidays, if I can work this out. Okay, so fix my glitch there. Over the holidays, if you scroll down the bottom, you'll see the holiday homework we've got here. So what we want you to do is to go back and really get hone in on that all the stuff we've learned about our skill classification and also our biomechanics. Make sure you go over all those Ed Rollo progress checks and know that user feedback we've provided to you through SAC1, and really look at what you can improve in those areas. The second bit of homework we've got for you guys on the holidays is to actually do the Ed Rollo lesson on what you've just watched this video as well. So go and consolidate your knowledge and understanding through that as well. Last thing for online lessons, I know you've already been told this, but at the bottom of this page you can see it's like our role. You've got to ask yourself, have I watched the video and seen the holiday homework? I'm from Wantirna South, so I press yes I have, and I press vote. So please make sure you do that. And there's my son. Say bye, Corey.
Bye.
See you guys. Have a good one, and we'll chat to you next term. See ya.